Hello, my friends. Welcome to discussion on momentum. Today we'll be talking about this thing called conservation of momentum, and it's something you've been learning about over the last few days in the lab, and hopefully we have a pretty good grasp of it. But today we're going to kind of formalize it with some quick notes here. So, conservation of momentum is a topic we're talking about today. And we've run into this word before, conservation, before, and we'll reinforce what it means today. But there's also, you've learned especially in chemistry, conservation of mass, conservation of the number of atoms. There's the conservation of energy that we learned about in freshman year. And all these conservation words in science mean the same thing. And what that means is the value before is equal to the value after some event. So if we take the total momentum, let me erase that. If we take the total momentum before an event, say in a collision, and we look at the total momentum after, these two things are always equal if there's no outside forces acting on the objects. So if it's just the objects doing something with each other, there's some event, the momentum before is equal to the momentum after. So to write that in sort of a shorthand, we can say that the mv total before is equal to the mass times velocity total after. Now this word total could be substituted with net as well, so the net momentum before and after is equal to each other. And this little equation right here can get really complex, but it boils down to this idea that if you start with a certain amount of momentum, the total of your momentum after has to be equal to whatever you started with. You can't gain momentum or lose momentum. The only way you can gain or lose momentum is there's some outside force pushing on you. In reality, even when that happens, if you step back a level, then that thing that's pushing on you, it gained momentum opposite of your momentum. So that momentum is really always conserved in all situations. So let's look at some examples of what this means to help us understand some of this. Let's start looking at a cannon. So here we have, I'm going to have a very badly drawn cannon. So here, sort of, a cannon, and it's on a wheel, and there's an axle, and here's a big cannon. I'm actually pretty happy with this cannon. It's got a hole in the middle of it, right? Going down the middle. And down here, you can't see it. I'm going to draw it, but you wouldn't really see it. Is a cannonball. And behind a cannonball is a bunch of gunpowder. So there's a pack of gunpowder down here. And this cannonball, of course, is going to explode. It's going to push the cannonball out the end of the cannon and about that far. So we don't have a very powerful cannon, but that's okay. So what we have to ask ourselves here is, if this is true, this conservation of momentum thing is true, that means the mass of the whole system, right, and velocity times velocity, the momentum here, and this is the before, has to be equal to the total momentum, mass times velocity, after. So let's take a look what that means. Now before the momentum, if we look at it, before the explosion, nothing's moving. So all the velocities are zero. Velocity of the cannonball is zero. Velocity of the cannon is zero. So the momentum before is equal to zero. That must mean the total momentum after has to also equal zero. And that's after the explosion. Now you might say, well, Mr. Haza, that's crazy talk, because obviously the cannonball is going to be moving really fast and it has mass, so it's going to have momentum. But the thing we have to look at is, after the explosion happens, there's going to be two momentums. The explosion is going to happen. The cannonball is going to be pushed forward. The cannon is going to be pushed backwards. And their two momentums have to be accounted for. So we say here that zero, the momentum before, is equal to the momentum of the cannon, so the mass of the cannon and the velocity of the cannon, plus the momentum of the cannonball. So that's the mass of the cannonball, velocity of the cannonball. Now we can see if we do this, we just subtract this from this side, and we can say that the mass of the cannon, negative mass, is equal to the mass of the cannonball, the velocity of the cannonball. So conservation of momentum tells us that the momentum of the cannonball has to be equal to the momentum of the cannon, but opposite in direction. So the cannon is going to fly back this way, and the ball is going to fly forward that way. Now we can do some quick analysis of this and take a look at it. If we look at the mass of the cannon compared to the cannonball, the mass of the cannon is huge. So over here we have a huge mass of the cannon. And over here the cannonball's mass is small, so we have a small mass for the cannonball. And the only way for these two to be equal is if the velocities balance out. So wherever there's a huge mass here, there's going to be a small velocity of the cannon. And when there's a small mass here for the momentum to equal out, that means that the velocity of the cannonball must be really big. Right? So even if you could make a super lightweight cannon that you could roll along with yourself, you would not want a super lightweight cannon. Because if this mass was small, like the velocity of the mass of the cannonball, that would make this velocity of the cannon much, much bigger. And you'd find that you'd shoot the cannonball out the front, and the cannon would shoot backwards and hit you. And that's why we try to make heavy cannons, even heavier than we have to necessarily, to be able to get a big mass here so that their recoil velocity, how fast they move backwards, is going to be minimized. Okay. Now there's another way of approaching this. Instead of going through conservation momentum, we can look at forces real quick. When this explosion happens, the force forward is equal to the force backwards. You can't push forward without pushing backwards. The explosion doesn't know which way forward is. So it pushes the cannon backwards, cannonball forward. And of course, because the cannonball has less mass, it's going to have a greater acceleration, leading to a greater velocity. The cannon is going to have a large mass, so it has a small acceleration leading to a smaller velocity. We get to the same conclusion either way. The cool thing, though, is that these two have to exactly balance out. So if you get a cannonball here that's 1,000 times less massive than a cannon, you end up with a velocity that's 1,000 times bigger than the cannon's velocity. So you get a very small backwards velocity and a very big forward velocity. And that's kind of the ratio you're looking for. So you're shooting the cannonball forward without shooting the cannon backwards very much. Awesome. So that's momentum, conservation of momentum with a cannonball. This same idea works with a gun as well. Let's look at a few example problems with some numbers in them. Let's say that we have two carts, like we did in the lab. We have these two little carts, and one's traveling at 2 meters per second and has a mass of 100 grams, and the other one is traveling or is stationary. So it starts out at 0 meters per second, and it has a mass of 300 grams. This cart's going to whack this cart, and they're going to stick. So here's the after. We've got them all stuck together. And this one again is the 100. This is the 300 grams. And the question now is, what's the final velocity? How fast will they be going? Now to do this, we can use conservation of momentum. So the momentum before, mv, the total momentum before, is equal to the total momentum after. So before we have two objects with two momentums. So we can say here, so the momentum of one, and we'll call this cart 1, cart 2. The momentum of, or the mass of 1 times the velocity of 1 is that momentum, plus the momentum of 2, which is the mass of 2, velocity of 2, is going to be equal to the momentum after. Now these two things are stuck together, so they act like one object. So we can say, hey, the mass of this one object is really the mass of 1 plus the mass of 2. And that's all times the final velocity. So that's our momentum conservation equation. For every different object, you have to account for its momentum. Here there's two objects, they stick together and make one object. And we have a final velocity of that one object. Now there's a couple ways of doing this. I'm going to show you how to do it algebraically without throwing in numbers quite yet. And then you can do it if you wanted to, you could put numbers in and figure out some stuff. right away we can see this thing's not moving right here. So this whole component, let me not do it that way. Let me back up. I'll keep that in there for just a more second more so we can see the math, how it works out. So plus M2 V2, right? And these are my befores and these are my afters. So to get the final velocity by itself, I'm going to divide by this quantity, M1 plus M2. Now if I divide that side, I got to divide this side, M1 plus M2. These two cancel out, and I find that, hey, the final velocity of this stuck together mass over here is equal to M1 V1 plus M2 V2, the sum of the starting momentum, so the momentum of this plus this, divided by the total mass of that object over here. Okay. And at this point, let's plug in some numbers and get some answers. So we have 200 grams times 2 meters per second for this first part. That gives me 200 gram meters per second. And that's plus 300 times 0 is, of course, 0, all over 100 plus 300 for the total mass, for a total mass of 400 grams. Now, if we do this, we say, okay, bam, bam, and we find out here that 200 divided by 400 is equal to 1/2, and the only units left are meters per second. So when we collide this thing in, you can see that we've lost 3/4 of its velocity because we had some of that velocity was used to accelerate this 3 times heavier object here. And that's how we run problems with conservation of momentum. Okay, let's look at one more and see what happens. So this time, let's let both of them start out moving. And let's say that we have a cart or some object, and it's going this way at 3 meters per second, and the mass of 100 grams again, nice and easy. And this time we have another cart here going 6 meters per second, and its mass is 200 grams. And they're going to collide with each other. And after the collision, they're going to stick together. Bam. And the question is, which direction were they going and how fast? So what's the final velocity? Now the sign of the velocity, whether it's positive or negative, will tell us which direction they're going. And we should actually make this guy a negative 6 meters per second, so just going backwards. And here the 100 grams and 200 grams. Now this negative velocity thing here is going to be really important when you start doing the math. Make sure you're accounting for those negatives. So the momentum before, M1 V1, is equal to, plus M2 V2, and these are all before, is going to be equal to the momentum afterwards. So the momentum here again is just M1 V, is the total mass, which is M1 plus M2, these two masses, times the velocity final. Now again, I'm just going to divide both sides by M1, M2. M1 plus M2, and I find that's my final equation right here. Now as I add these in, I find that 3 meters per second times 100 grams is 300 gram meters per second. Plus, I take 200 times 6, and that gives me 1,200. Notice it's negative here. Negative 1,200 gram meters per second. And all of that is divided by sum of these two, which is 300 grams. Now before I can divide, I got to take care of this math on top. Oops, and that's equal to the final velocity. Take care of this math on top. I end up with a negative 900 gram meters per second divided by 300 grams. Equals the final velocity. Grams cancel. And I have 900 divided by 300. Of course, that's a 3, and it's a negative 3 meters per second. So when I look at this negative 3 meters per second, I say, okay, so this chunk is moving that way at a velocity of 3 meters per second. Bam. So that's a quick and dirty explanation of how to do momentum. The idea is you catalog the momentum before, and it has to be equal to the total momentum after. Awesome, good luck.